Hi, today I'm going to talk about some divisibility tricks that you can use to make dividing numbers a whole lot easier. So say you're presented with this long, massive number, or even a short number, and you have to divide it. And you wish, wasn't there an easier way to just see what numbers divided it? Yes, there is. There are a lot of tricks that you can use to see if a number is divisible by any digit from 1 to 10. And today, I'm going to go over what each of those tricks are, and then later, how they work. So let's start just with 2, right? This one might seem kind of obvious, but if a number is even, meaning its last digit is 0, 2, 4, 6, or 8, it is divisible by 2, right? So just even. Now for 3 is a little interesting. If the sum of the digits in a number are divisible by 3, then that number is divisible by 3. So for example, 27, 2 plus 7 is 9, which is divisible by 3. So that means 27 itself is divisible by 3, which we can check it is. It's 9 times 3. So, sum of digits. For 4, we see a rather interesting pattern here start to emerge, where now instead of looking at the last digit, just like we did for 2, we're going to look at the last 2 digits. And if the last 2 digits are divisible by 4, then that number itself is divisible by 4. For 5. Now 5 is another pretty simple one. All numbers that are divisible by 5 either end in a 0 or they end in a 5, right? 20, 25, 30, 35. Because it's either, a 10, which is divisible by 5, or just a straight 5, right? So either a 0 or a 5, the last digit, means it's divisible by 5. For 6, we actually don't need a rule for 6, because 6 is just 2 times 3, which we already have rules for. That's nice and quick. 7 doesn't really have a nice, clean rule. It's kind of uninteresting. And besides, there are more interesting patterns, like 8. 8, and this is where things get a little fun. First, we're looking at the last digit for 2. Then, for the next power of 2, which is 4, we're looking at the last 2 digits. And now for 8, the next power of 2, we're looking at the last 3 digits. If the last 3 digits are divisible by 8, then that number itself is divisible by 8. Pretty interesting. And then finally 9. And 9, another very interesting pattern, which is 9 is 3 times 3. Well, 9, the pattern is, you do the same thing that you did for 3, but you have to check to see if the answer itself is divisible by 9. So, sum of digits. And those are all the rules for all the numbers that have nice, quick, and easy divisibility tricks. So if you're presented with a very, very large number, or you have to factor, for example, and you want to know, what is this number divisible by? You can use these tricks to say, okay, it's divisible by 9 and 4. That's good to know. And then just start factoring or start dividing, right? Now, let's get into how these work. So, I'll start with 2, because even though it may seem very simple, and to be fair, it kind of is, it does reveal the pattern that we're going to use to find out and derive much more of these. So, a number is divisible by 2 if and only if it's equal to 0 mod 2. And this mod refers to modular arithmetic. If you don't know about that, I highly recommend you check out my video on that. But essentially, modular arithmetic is a lot like working with remainders, right? So what this is basically saying is that when I divide this number by 2, I'm going to have a remainder of 0. Or in other words, this number fully divides 2, leaving nothing left. Right, so say I have a massive number. I'm going to say 8, 9, 6, 5, 8, 4, 1. Right? We can write that as 8, 9, 6, 45840 plus 1, right? We'll still get the same value. Now, why would I do that? Well, because this number has the same modular value. I do this to denote a modular value of this is the same modular value as this mod 2. You might say, well, why is that? Because this ends in a 0. So that means this is divisible by 10. But we also know that 10 itself is divisible by 2. 2 times 5 equals 10. Right? So what this really means is that this is divisible by 2. Of course, we know this isn't. Right? So what we can say here is that, oh, then this must not be divisible by 2 since both parts aren't divisible by 2. You may say, well, what was the point of that? Well, we know from the end, right? We can conclude that since, 2 divides numbers that end in 0, right? And they don't divide numbers that end in 1, we can say, hey, we can expand this pattern so we can test just the very last digit, 2, 4, 6, 8, or 10. And we went through this very long method showing that, 2 divided by this number ending in 0, we can do the same thing for other digits, for 2, for 4, for 6, for 8, for 10. Now, let's move on and let's consider 4, because 4 is built up of much of the same thing, right? So, how are we going to do that? Well, 10 is not divisible by 4. 100 is, right? 25 times 4 is 100. So, a number is divisible by 4 if and only if its last 2 digits form a number which is divisible by 4. For example, let's take this 45376 number. I'm going to rewrite it as 45300 plus 76. Right? I'm going to take the modulus of that. Now, I can split this up into 2 parts, right? This part and this part. I know this part is divisible by 4 because it's divisible by 100, because it has these 2 zeros here, and 100 is divisible by 4. But this last part, I'm going to have to test. If this is divisible by 4, then my whole number is divisible by 4. And I can use this pattern of splitting things up for any number to test if it's divisible by 4. And that's why we look at the last 2 digits. Because we can separate these out. We can separate this out into 0, 0 plus the last 2 digits. And by testing the last 2 digits, we can determine if our number is divisible by 4. Right? So that's why we use the last 2 digits, because we have this 100 part that we know is divisible by 4. And if this part's divisible by 4, then the whole number is divisible by 4. And of course, we can repeat the process for 8, except this time 8 isn't divisible by 100, so it's divisible by, so the next and nearest power of 10 would be 1000. 8 is divisible by 1000. And we repeat the same process. I can just do 4, 5, 3, 6, 7, 6, right? And I can rewrite that as 4, 5, 0, 0, 0 plus 3, 7, 6 mod 8. We know this is divisible by 8 because it's divisible by 1000. And the only question is, are the last 3 digits divisible by 8? Because if they are, this whole number is divisible by 8. So that's the pattern we're used to determine they're divisible by 8. So that's the 2, 4, and 8 taken care of. What about the 3? What's going on with the 3? So, we use a slightly more complicated method of modular arithmetic to find the 3. Let's use 7, 9, 6, 5 as a number. Right? We can divide it into 2 parts. Not just into 2 parts, but many more, like we did, more than what we did in other parts, right? We can say it's 7,000 plus 900 plus 60 plus 5. And since 10 has a remainder of 1 when you divide it by 3, it's 1 more than 9, which is itself a multiple of 3, then, for any other power of 10, right, 10 times 10 or 10 times 10 times 10 is still going to be 1 mod 3. Now, why is that useful? Well, we can rewrite this as 7 times 10 to the 3 plus 9 times 10 to the squared plus 6 times 10, and so on and so forth. And you may say, well, why would I want to do that? What's the point in doing that? Well, if I were to take the mod of all this, all these 10s would become 1s, right? Since 10 is equal to 1 mod 3. So I'd have now, instead of 10 squared, I'd have 1 times 1 times 1, which is just 1. So I'd have 7 now, plus 9, plus 6, plus 5 mod 3. Now if this is divisible by 3, this will just become equivalent to 0 mod 3, and I know my number will be divisible by 3. But these are also the sums of the digits in my number. So we can see here, hey, if the sums of my digits in my number are divisible by 3, if they come out to produce 0 mod 3, then my number is divisible by 3. So we do it in this example, right? 6 plus 5 is 11. 9 plus 7 is 16. We'll see that's equal to 27. 27 mod 3 is 27 divisible by 3? Yes, it is. So that's equal to just 0 mod 3. So we can say, yes, this number is divisible by 3. And that's where you can do the sums of the digits of a number to get their divisibility value. So if the sums of the digits are divisible by 3, then your number itself is divisible by 3. Now, what are we going to do to find the divisibility of 9? Because we know it operates under the same basic principle, right? How are we going to get that? Well, we'll kind of do the same method of breaking it up, right? Except this time we're not going to use 10s. We're going to try a little more, cheeky way of doing it, right? So we can take what's a sufficiently massive number to do it on. Okay, I guess 7, 9, 6, 5, 8, 4, 1. Huge number. Well, that's equal to 7 times a whole bunch of zeros, or alternatively a whole bunch of 9s plus 1, which will get you a whole bunch of zeros. So right, and we continue that pattern where it's 9 plus a whole bunch of 9s and so on and so forth until we eventually get plus 1. Right? Now, why did I do this? Well, if I mod it out by 9, right, if I did mod 9, all of these big 9s would just vanish, right, because they are divisible by 9, so they just become 0. Right, so what I'd be left with is 7 times 1 plus 9 times 1 plus so on and so forth until I get to 1, all mod 9. And if this whole sum is divisible by 9, this becomes 0, and I'll know that this number is divisible by 9. If not, it's not. And as you can see, this right here is equivalent to the sum of the digits in this problem. So, using this modular arithmetic, we know if the sum of the digits in my problem are divisible by 9, then my number is divisible by 9. And those, my friends, are all the divisibility tricks. I hope you found that helpful. I hope you can now look at the number and say, aha, I know the divisibility to this. And I hope you have a great day.